Hello everyone, this is Professor Roman. Welcome to the 47th video in my video lecture series, An Introduction to Discrete Mathematics. So this time we will talk about Huffman codes. When a character such as a letter, a digit, or a punctuation mark is entered into a computer or sent over some form of transmission line, even sent through space from a satellite, it's converted into a binary word for transmission purposes by means of what is called a character code. One of the most common character codes you may know is the basic ASCII code, ASCII. In this character code, each character is encoded by a binary code word of length 8. This is the original basic ASCII code, not the extended ASCII code. But the relevant point here is not the ASCII code, it's the fact that this code, along with many other commonly used codes, have the property that each character is given a code word of the same length. Those codes are called fixed length character codes. Now, fixed length character codes have advantages and disadvantages. One of their advantages is that we don't need any special characters to separate the characters in the message, the code words in the message. All we have to do, for example, in the case of an ASCII message, is divide the string into 8-bit segments, and we know that each segment is the code for a character in the message. So it's simple. We know when each code word ends, we know when the next one begins. But one of the major disadvantages of using a fixed length character code, such as the ASCII code, is that the characters that are used very frequently, such as the letter E, at least in the English language, have code words that are just as long as characters that are seldom used, like the letter Z. But a character code that encodes frequently used characters with fewer bits than infrequently used letters, which get longer code words, can save a great deal of time and space. These are called variable length character codes. But there is a problem with variable length character codes. It may not be possible to tell when one character stops and another one starts, or more appropriately, when the code word for one character stops and the code word for the next character begins. And we can illustrate that problem very easily. Here is, let's say we have a character set C consisting of the first 5 letters in the Roman alphabet, A, B, C, D, E, F. And suppose that A and B are the most frequently used characters, the rest are less frequently used. So you set up a variable length character code. A is coded as 0, B as 1, because they're the most commonly used letters, so they get the shortest possible code words. C through F are given 2-bit code words. Well, this code is very efficient in the sense that individual code words are as short as possible given their probabilities of occurrence, but what does this message say? 0, 1, 0, 0, 1, 1. Does it mean A, B, A, B, B, A, B, A, B, B, Or does it mean DCF? Or does it mean ABADB? All those strings I've just given you, if you encode them, you will get this message, coded message. So as it stands, this variable length code is useless. It's full of ambiguities. Now we could resolve that issue by using a special character to separate the code words. I used the slash here, and this is unmistakably decoded as DCBB. But adding that character, first of all, makes the messages longer, which is what we're trying to avoid, and causes other problems. How do we encode the separator? And then how do we tell in a message when the separator appears and when it's over, the end of the separator? So this is not exactly the best solution. And we need to be very careful when designing a variable length character code to avoid the problems of ambiguity. Well, fortunately, there is a way to do that, and we're going to discuss that now. You see, the problem with this character code here, and this is more than just the character code. The character code is on the right. This whole thing is referred to as an encoding scheme, and I'll talk about those in a little while. The problem with this encoding scheme is in the character code itself, because a code word for one character may be the prefix of a code word for another character. So 0 is a prefix of 00 and 01. So if you just had 001, let's say you just had 000, would that be AC or would it be AAA? You cannot tell when one code word ends and another code word starts, because the first string might just be it might be a code word as well as a prefix of a longer code word, and there's no way to tell. So that is the problem. Well, we can fix that by avoiding codes in which one code word is the prefix of another code word. So a character code, I'm just going to call it a code, that has the property that no code word is the prefix of another code word is said to have the prefix property. And this property totally eliminates the ambiguity problem, because we know that once we've recognized a code word, we can stop and say that is the code word that was sent. It cannot be the beginning of a longer code word. So this means that code words can be interpreted or decoded as soon as they appear in the message. You don't have to wait to get the whole message before you can start decoding in order to read the message. There is another term for this. A code is said to be instantaneous if whenever any sequence of code words is transmitted, each code word can be interpreted as soon as it is received. We don't have to wait any longer. And I'm going to leave it to you to show that a code is instantaneous if and only if it has the prefix property. So let's consider an example. here's a character set, CEORT. I don't know why I chose that, whatever. And here is an encoding scheme. Here is a character code on the right of each arrow. This character code has the prefix property. No code word is the prefix of another code word. So this message, for example, can only be decoded in one way. The first two bits 1, 1 must decode to C because they are not the beginning of any other code word. And you can do the rest of the decoding yourself if you're interested. I have no idea what this message says. Probably something very pithy. Well, in designing a character code, we want it to have the prefix property. Otherwise, it's essentially useless. But we also want a variable length character code to be as efficient as possible in the sense of using as few bits as possible, because more bits means more time, more space, more expense. Now, no code will be the most efficient for all possible messages. So the best we're going to be able to do is find a code that will be the most efficient on the average. And in order to put this more precisely, we have to have some idea of how frequently each character in the character set occurs in messages of the given language, whatever it might be. And the way this is done is, well, one way is to assign each character a frequency. So, for example, for this character set, ABCD, the frequencies might be 2 for A, frequency for B is 2, C is 8, D is 5. I just made those numbers up. These numbers have no absolute value. They're only relative values. So what this means is that for every 2 occurrences of A, there are going to be 8 occurrences of C, 5 occurrences of D, 2 occurrences of B. So they're relative numbers. You could double all these and it wouldn't change the frequency distribution because we're only comparing them. Okay. And I'll say more about that in a little while. But in any case, for this frequency, C is the most commonly occurring letter, 4 times more common than A or B. Using the frequency of each character in a character set, call it the frequency distribution, we can define the concept of the weight of a character code, which is a numerical description of how efficient the code is. And again, this is a relative measurement. So here's the definition. We have a character set, S1 through Sn, and we have frequencies for those characters. And suppose also we have a character code for this character set, and the length of the code word for a given character, Si, I'll denote by L of Si. Then the weight of the character code is defined to be the weighted sum of these products, the frequency of the symbol Si times the length of its code word. So we're weighting the code code word lengths by their frequencies. Let's take a look at an example. Here are two encoding schemes, two different codes, same characters. Let's say these are the frequencies. Now, suppose I just showed you this at the beginning of the video. So we didn't have any background. And I said to you which code, which encoding scheme looks more efficient. Well, you might look at the number of bits that the codes use, 2, 3, 6, 10 here, 5, 7, 9, 11 here. So code 2 uses an extra bit. That's a mark against code 2. Maybe code 1 is more efficient. You might look at the largest or longest code word. Here it's only 4 bits, here it's 5 bits. Another strike against code 2, looking better for code 1. But you might also notice that in code 2, the most frequently used characters, C, for example, and D, have the shortest code words. On the other hand, that's not the case for code 1. D is the second most commonly occurring character, but it gets, in fact, the longest code word. Well, all this is fun and games. What we really need to do is compute the weights of the two codes, and that will tell us. So code 1 has weight 50, code 2 has weight 40. So code 2 has the smaller weight, and so on the average, it will use fewer bits to encode messages. And so it is the more efficient code, despite the fact that it uses 11 bits total instead of 10 and has a longer code word. Maximum code length is larger. None of that matters. It's the weight that matters. And these numbers, 50 and 40 again, mean nothing in absolute terms. It only means that code 1 is 5/4 more efficient than code 2. Now, one thing to note about frequencies, as I have been belaboring, is that they are relative values. Their absolute values mean nothing. And the weights are the same problem. They're relative numbers, not absolute numbers. So to say that a code, for example, has weight 40 means nothing. You have to say it in comparison to another code which has a weight 50, for example. Well, in order to avoid this issue, see, again, if I were to put zeros at the end here and this was weight 500 and this was weight 400, it wouldn't change the relative efficiencies of the two codes. So to avoid that sort of thing, we can normalize the frequencies by dividing by their sum. So here are these frequencies again. The sum, if I did this correctly, is 17. And so we normalize by dividing by 17, and we get these numbers. And I change the symbol from F to script P because now we have a probability distribution. These are non-negative numbers that add up to 1. in general, if f is a frequency function for a character set, then we can convert to probabilities the probability of a symbol sk is its frequency divided by the sum of all the frequencies, and we get normalized frequencies, or better known as a probability distribution for the character set, for the relative frequencies of the character set. And because frequencies are relative values, and when you scale them it doesn't change anything, it is often easier, especially in practice, to work with the corresponding probability distribution. And the weight of a code now is replaced by the normalized weight, which is called the average code word length, because that's what it is. You take the length of each code word, you multiply it by the probability of its occurrence, and you get the average code word length. Okay, let's move on to a couple of concepts: information sources and encoding schemes, a term I've been using. A character set by itself is not sufficient to design an efficient code. You've got to have the frequencies, or equivalently the probability distribution. So this leads to some definitions. An information source, sometimes just called a source, is an ordered pair, script S, which has a set S, that's the character set, along with script P, which is the probability distribution for the character set. Now, normally, as far as I know, sources are not ordered sets, but I have decided that that would be useful in our discussion. It's not essential. I could have worked around that, but the wording would have been more complex later on, so in fact, I did this originally, then I changed my mind and went to non-ordered sets, then I changed my mind a second time and went back to ordered sets. So it's not important, it's just helpful to order the source symbols. Okay, and I'm not talking about order in the sense of S1 is smaller or bigger than S2. I'm just placing them in an ordered Q tuple. So in that sense, there's an order on the source symbols and corresponding probabilities. And this is, in fact, one reason why I did this. If these were curly brackets in both cases, you would have to assume that P1 was the probability of S1 occurring, because we have subscripts that match. Both subscripts are 1. But if I wrote this as ABCD, then it gets a little problematic. If I wrote this as ABCD and these probabilities as various numbers that add up correctly, the only way you could tell which probability went with which symbol was to assume these were ordered. So that's why I'm ordering them. So I could use little p sub k for the probability of S sub k. Now, I can also assume, without any prejudice, loss of generality, that the probabilities are descending or not ascending, okay? And that I just do that by reordering the character set if necessary. And that'll be convenient as well, and we're not losing anything by doing that. Now, an information source can also be described by an order pair character set frequency function. And when we come to Huffman codes themselves, we're actually going to use the frequencies, okay, because that seems to be traditional for Huffman codes. So that's the definition of an information source, a source alphabet, and the corresponding probability distribution. And if we have an information source and a set of code words, otherwise known as a code, an encoding function is a bijective function that takes source symbols and returns code words. Has to be bijective. You don't want two different symbols to be encoded with the same code word. Now you're going to have trouble decoding the message. Okay. This is the process of moving from source symbols to code words is called encoding. The ordered quadruple now, the character set, the probabilities or frequencies for the characters in the character set, the code you're using to encode the characters, and the function that does the encoding. All of this is called an encoding scheme. Looks like a lot. I understand. The more you live with it, the easier it will become. The average code word length is what I wrote before. I've just written it in a little different language here. You take the length of the code for the symbol SK, that's E of SK, gives you the code word. So the length of the code word for SK, I said code a minute ago. I should always say code word, but I'm going to slip once in a while. The length of the code word times the probability that the symbol occurs. In other words, probably the code word occurs. Add them up. That's the average code word length. And sometimes I'm just going to write it this way because it's easier to read. Okay. This, of course, is more informative. You know exactly what I'm talking about, but this is less cluttering. So I'll use them both. Also, I'm going to set some notation so we can talk about these things without having to repeat this means this over again. So the source symbols are S1 through SQ. The probabilities are P1 through PQ. The code words in C, the code, will be C1 through CQ, and their lengths will be M1 through MQ. In case you're wondering about all this terminology, the study of fixed length and variable length codes, encoding schemes, information sources, and all this, it's quite interesting, really, when you get into it. It belongs to a branch of mathematics known as information theory. Now, there are some things that we can do to an encoding scheme. We can tweak the scheme. We can tweak the encoding function and the code. We'll do both one at a time in order to produce another encoding scheme that has better average code word length, which is desirable. So first thing we can do is improve the encoding scheme by improving the encoding function. Same code, same source, source alphabet, S, same probabilities, P, Same code, C, same set of code words. We're just encoding differently than in the original encoding scheme. How do we do that? Well, the average code word length is this number. I have changed this summation to, I've written out the sums and used the notation in this table. Length times probability. Okay. Now, if for I less than j, so for one term here, the I term and the j term, okay, maybe I should have added those in here. Okay, they appeared like magic. If for I less than j, m sub j, now remember how the probabilities work. They get smaller as we read from left to right. P1 is the biggest probability, the most frequent source symbol, S1, least frequent source symbol, SQ. So for I less than j, if mj is smaller than mi, we've associated a shorter code word with something less common and a longer code word with something more common. Stupid. At least not good for the average code word length. If we swap the two, mi and mj, we will improve, or at least not reduce, will not make worse the average code word length. We may improve it. It may stay the same if pi and pj are equal. Okay. But if pi is strictly bigger than pj, the swap will reduce the average code word length. It never increases it, but it could reduce it, and frequently will reduce it. So what does it mean to swap the two? Well, the code word lengths we're swapping here, but what we're swapping is the encoding of those two code words. So instead of the code word associated with SI having length MI, it will have length MJ instead, because we swap the two code words. That is a re-encoding. It's a changing of the encoding function from what I called E to E prime. And E prime and E are the same except for these two source symbols. The code words for those two source symbols get swapped. And so now MI is, the new MI is less than or equal to the new MJ. And we can keep doing this. We can keep re-encoding until the code word lengths go in the opposite direction as the probabilities. Larger probabilities, P1 is the largest, gets the smallest code word, shortest code word, I should say. The least frequent symbols, probabilities PQ, PQ minus 1, and so on this end, get the longer code words. So I'm going to refer to this whole process, we get down to this point, as re-encoding the original encoding scheme. All it is doing is changing the encoding function, not the code. If the code had the prefix property before, if it was instantaneous, it's still instantaneous. And we can say that the re-encoding produces an encoding scheme that has the smallest average code word length among, and this is important, among all encoding schemes that use the same source and the same code. So this is a limitation here, and it's not going to be enough, which is why we got to do some more work. But at least we've made significant progress. The next thing we need to do, once we've done the re-encoding, and if the encoding scheme is instantaneous, the re-encoded, if the original was instantaneous, so is the re-encoded scheme. So this is the re-encoded scheme now. I'm just going to use the same symbols and to cut down on the number of primes. So this is, we assume this has been re-encoded. So the code word lengths satisfy this property. Okay. So what we're going to do is, unlike the re-encoding procedure that did not change the code, is we're going to change the code. Specifically, we're going to change the last code word, CQ, the one that has the longest code word length associated with the least frequent source symbol. Before, all we did was rearrange the code. We didn't change any code words. Now we got to change a code word. So what we're going to do is replace, if necessary, the last code word CQ by another code word, CQ prime. And we're going to do that so we get two properties. First of all, the previous code word CQ minus 1 and the new CQ prime have the same length. And that'll be the maximum length in the entire code. Okay. So MQ minus 1 will equal MQ. So just to put this in concrete terms, if CQ had length 10, CQ minus 1 was length 9, we might have other code words of length 9. We're going to chop a bit off of CQ, so it too has length 9. Okay. Also, we're going to arrange it so that CQ prime not only has the same length as CQ minus 1, but that these two words differ only in their last bit. So they're almost the same code word, only the last bit. One has a 0, the other has a 1. Well, to see how to do this, if C, the code, already has two maximum length code words that differ only in their last bit, there's nothing to do. Except if they're not the code words CQ and CQ minus 1, we do another re-encoding, change the encoding function, and push those two to the end. Because we're dealing with code words that are the same length, if you interchange two of them, it doesn't change the average code word length. So let's assume that's not the case and we have work cut out for us. Now, one possibility is that CQ is the unique code word in C of maximum length. There are no other code words of that same length. Then what we can do is first chop off CQ, keep only the prefix of CQ of length equal to the next largest code word length, MQ minus 1. So again, CQ has, say, length 10. All the other code words are shorter. Say the second longest one is length 7. Then we chop off the last 3 bits of CQ and bring it down to length 7. Now that is not a code word in C. That chopped off code word doesn't already appear in C. And that's because C has the prefix property. We're taking a prefix of CQ of a certain length. That is not a code word. Otherwise, it would be the prefix of CQ. It's also not a prefix of another code word in C, because the chopped off code word now has maximum code word length, which I think I said was 7. A code word of maximum length can't be the prefix of another code word, because that other code would have to be longer. So in this case, where CQ is unique code word of maximum length, we can replace CQ by CQ prime. We can chop off some of CQ at the right end, and now have 2 words of maximum length, and we'll call, and rather than using the primes anymore, I'm just going to refer to CQ minus 1. That never changed. That's the same as before. And I'm going to call this CQ prime, this prefix, I'm just going to call it CQ from now on. So assume it's done, relabeled as CQ. I don't want to have C1 through CQ minus 1 and then CQ prime. So now we have a code where MQ is equal to MQ minus 1. Okay, take a deep breath. If the new code word, which I'm now calling CQ instead of CQ prime, differs only in the last bit with one of the other code words, it could be CQ minus 1, but it could be another code word of maximum length. Let's call that D. Oops, sorry. Then we can again re-encode, and so that D will now take the place of CQ minus 1. They'll swap with CQ minus 1, and we're done. Okay. Because of the difference only in the last bit. And this doesn't change the average code word length. So what remains is to assume that CQ, the new CQ, the shorter version, differs with every other code word of maximum length in a bit other than the last bit. And since all the other code words have that property, I used to be able to type much better than I can now. Every pair of code words of maximum length has this property. Every pair has a difference somewhere other than the last bit. You could say they're internally different. It's not the last bit that makes them different. The last bits may be different, but they're different from another source and somewhere else in the word. So not to get any more confused than you might be already, let's make a list of all of the code words of maximum length. And here's CQ down here, and it's length MQ, which is also MQ minus 1, because that's what we did. We chopped CQ down to be the same length as CQ minus 1. Each pair of words in this list differs at some bit other than the last bit. Now, let's take CQ minus 1 and make a little change. CQ minus 1 prime, all we did is change the very last bit, And there's only one way to change a bit. You change it from 0 to 1 or 1 to 0, so that's what I'm saying here. So this is no longer equal to CQ minus 1. But it's the same as CQ minus 1 until the last bit. Now this word CQ minus 1 prime still has maximum length, MQ. We haven't messed with the length. It's nowhere on this list. And I'm going to let you think about that. This is not easy to follow. I understand that. It took me quite a while to write this up, in fact, to try to figure out how best to explain this. I don't know if I've done that, but I tried. Okay. So this new CQ minus 1 prime is not a code word in C, nor is it the prefix of any code word in C. And again, that's something you should think about if you're interested in this. So we can replace CQ by CQ minus 1 prime without changing the average code word length. Well, then we're done, because CQ is now this word, which is the same as CQ minus 1, except in the last bit. That's what we've been trying to do. Now, one last thing. If we want to, we can arrange it so that the last bit of CQ minus 1 is 1, and the last bit of the new CQ is 0. Or the other way around, just by swapping these two code words. Again, that won't affect the average code word length. Okay, that's just an arbitrary choice. Doesn't matter. The point is the last bits are different, and that's the only place they're different. So we're talking now, remember, about this is still in place, but CQ is now replaced by this. Well, we've got what we wanted. CQ minus 1 and the new CQ have maximum length, and they differ only in their last bit. So let's summarize where we are. We start with an instantaneous encoding scheme. The notation we're using is from this table. Then there is an instantaneous encoding scheme C prime. Could be the same as C if we don't have to touch anything, whose average code word length is no longer than that of C, and for which the following holds. The probabilities are in decreasing order, or I should say non-increasing order. That's something we settled before. Can always do that by reordering the source symbols. But now the code word lengths satisfy this property, again by re-encoding. But the new feature, the hardest one to get to, was that the last two code words look like this. They start the same, they only differ in the last symbol, the last bit. Now, I don't know what to call this code really, so this new encoding scheme C prime, so I'm going to call it a normalization of C. Seems reasonable. Okay. Also, for reasons that I can't explain yet but will become clear, I'm going to refer to these two final code words here that have the same length but differ only in their last bits as sibling code words. sister code words or brother code words or whatever, sibling code words. They are so similar that that seems like a reasonable term, but it's going to become more reasonable when we stick these at the vertices of a tree. They will be the children of a vertex, the same vertex. So in a sense, so they're children of the same parent, so they're siblings. Downstairs. Well, the video so far has run 50 minutes, and I really didn't want videos to run this long. We are finally ready to discuss the Huffman code and its encoding scheme. And as I said before, I do want to justify what I say about this encoding scheme. And that's going to take a little while. So rather than end up with an extremely long video, I think it's better to stop this video here, and we'll pick up the next video with the Huffman code itself. So thank you for watching. Sorry for the confusion, and I hope I see you in the next video.